Hello everyone. In this video, I will introduce our recent work all-in focus imaging from Event Focal Stack. When we take a photo, objects that are not on the focal plane suffer from defocus blur. Defocus blur is sometimes undesirable in photography, but the blur kernel varies with object depth, making it difficult to remove. In this paper, we propose capturing event focal stacks by recording the events triggered by an event camera as the focal point is moved through the scene. Due to the high temporal resolution of event cameras, event focal stacks encode information from all depths. Based on an event focal stack and a single blurry image, we design a three-stage method to achieve high-quality refocusing and all-in-focus imaging. The additional information provided by event focal stacks empowers our method to outperform other state-of-the-art methods. These are some refocusing and all-in-focus results. Our method is capable of recovering high-quality, all-in-focus images, as well as refocusing images to arbitrary depths. Let's start by introducing the defocus blur problem. When taking a photo with a traditional camera, we can only focus at a single depth plane, and seen objects at other depths will suffer from defocus blur. However, in many conditions, we would like to remove the blur and recover an all-in-focus image. There are many methods that aim to achieve single image-based defocus deblurring, such as DRBNet, iFan, KPass, and APL. Their input is a single defocused image, and their target output is a sharp all-in-focus image. However, they often fail to recover lost details as the setup is very ill-posed. The image focal stack method is to take a series of images at different focal distances and merge their sharp parts into an all-in-focus image. The problem is, when the number of images is small, some depth ranges may remain uncovered. But to take many images takes a lot of time, making the method unsuitable for dynamic scene. The focal sweep method sweeps the focal point through the scene in a single exposure, making the point spread function the same for pixels at all depths. It collects information from all depths, but the depth information is lost. To overcome these problems, we propose capturing event focal stacks. Event cameras are novel sensors that only measure motion in the scene. An event is generated anytime a single pixel sees a change in brightness larger than the threshold. Event cameras have very high temporal resolution, so if we record the events generated as we sweep the focal point through the scene, we can record information from all depths. Events encode the logarithm change of the latent intensity. For example, the summation of the events recorded when sweeping focal point from depth D1 to D2, AD1 to D2 is the logarithm difference of the latent images focused to D1 and D2. As a result, if we have an image focused at any depth ED1 and we want to refocus it to an arbitrary DK, we only need to get the events captured when sweeping from D1 to DK and add them up. In other words, a single image and the event focal stack together encode information from all depths. Based on this fact, we designed a three-stage algorithm for all-in-focus imaging. This is the pipeline of our algorithm. From a single image and an event focal stack, we select refocus timestamps, reconstruct an image focal stack, and merge it into a sharp image. The first step is to divide the image into n times n patches. We assume the depth in each patch is constant, so the reconstructed sharpness of the patch is a unimodal function to refocus time. For each patch of the image, we use the golden rate search algorithm to find the moment when it was in focus, getting n times n refocus timestamps. The second step is image refocusing. For each refocus timestamp, we use event refocus net to reconstruct a refocused image from the input image event focal stack, forming an image focal stack. We use a neural network instead of simple summation in this stage, because event cameras have spatially and temporarily varying noise, and neural networks can filter them out more robustly. The third step is merging the stack. We predict merging weights with event mergeNet using image focal stack and events as input. The events neighboring each refocus time are used as input because events encode sharp edge information and improve the quality of the weight. We merge the focal stack with weights to get all-in-focus results. The neural network model's event refocus net and event merge net used in the method are trained with synthetic data. Using Blender, we create scenes with random shapes and use random MS code dataset images for textures. We render high frame rate focal sweep videos with a large aperture and the all-in-focus ground truth with a small aperture. We use DVS voltmeter to simulate events from the focal sweep video, and we set the simulator parameters randomly to avoid model overfitting. Our test dataset is captured with a hybrid camera system. It is composed of an event camera and a machine vision camera. They are connected with a beam splitter. Here are some results of our method on synthetic data. This data is generated from the light field dataset ELF-DOF. Compared to the image-based methods, our method has additional event focal stack information as input, so it performs better. Here are some results on real data. Our method recovers sharp edges compared to other methods. Here are some refocus demos on synthetic data. By using the event focal stacks, the input images are refocused so that the patches in the white boxes are most in focus. Here are some refocus demos on real data. In conclusion, in this paper, we propose recording event focal stacks for high-quality, all-in-focus imaging, and we design a corresponding three-stage algorithm. In our paper, we also compare our method to dual-pixel methods and image focal stack methods, and ablation study results are provided. More information can be found on our project page, and future work will be posted on our lab page. Thanks for your time.